So welcome to the first class for the fundamentals of mathematics. So this is Math 52. So this is a logic class. So this class is about proofs. It's about an introduction to proofs and how to do proofs. There's kind of two ways to approach the subject. There's one that's very practical and kind of how to use math to do proofs. And the other one is kind of foundational, how to do abstract logic, set theory, things about infinite numbers, rigorous things like this. So I'm going to try and do both, but first and foremost, I want to teach you guys how to do proofs. So this class is a stepping stone to other more advanced math classes. So Math 52 is the proofs class. After this, you guys have algebra, real analysis, topology, all sorts of other cool math classes that you can take after taking this class. So that's the idea of this class, is to kind of give you somewhere to go. So I don't know if I said this, my name's Taylor, or Dr. Dupuy, or Professor Dupuy. You guys can just call me Taylor. Okay, and you guys are section 52B. So my email's on here. All the information for the course is going to be on the course webpage, including homeworks, this syllabus. Everything will be from there. I've written down two books. Let me get the books out. You see what they look like. Okay, so there's this book here. Is the book that you guys should have from the bookstore. It's by Lakins, or I think that's how you say it. And this is kind of the more practical point of view. Okay, there's this book here, which I'm going to scan the first chapter of. This is a more formal point of view. So this is like how to manipulate formal symbols, and it's a much more rigorous one. It's more philosophical. Okay, I'm going to use this from time to time as a reference. You guys don't need to get it, but it's interesting. So what I recommend is that you guys kind of find a reference that you like, and there's Khan Academy videos as well, and then these are going to be the videos are going to be posted as well for you guys to look at later. All right. So I guess you guys probably want to know about the grading. So there's going to be weekly homework. The first homework is going to be due Friday. I need to post it. This one is going to be a light one. And then there's going to be 2 exams and a final. Okay? So at the end, after you do all your homeworks, right, it'll be worth 1 exam. Okay? And then the final is going to be worth 2 exams. So it's 1 part homework, and then you have two exams, 2 parts exams, and then 2 parts final. Okay? So that's how it's going to work. There's one thing that's a little bit different from other classes, is that I have an exam dropping policy. So if you miss an exam, or you're sick, or for some reason you can't make it to an exam, what will happen is that I'll just drop the exam and you can make it up. We'll just replace that weight with the weight of the final. Okay? And because that's not fair to some people, so suppose someone just did badly on an exam and they would have been better off if they missed the exam. So what I do is I just say that at the end of the semester, you can say which exams you want to drop. Okay? So if you do badly on an exam and you don't want to count it, then it doesn't count. Okay? So the way that'll work is that I'll have a spreadsheet at the end of the semester, the last day before the final, and I'll ask you which ones you want to keep, which ones you want to drop, and then you guys just decide, which ones you want to keep and which ones you want to drop. Yeah.
So if you get, like, say, A's on all of them,
then,
all 3 of them, yeah, you replace half of the final with the best score of...
No. The final, you always have to take the final. But the thing is I really only care if you, like, the final, suppose you get an A on the final, right? And you did F's on the 2 other ones or something, right? Well, if you want to drop those 2 and bank on getting the A on the final, that's as good as, to me, it shows that you know the material by the end of the class, so, okay. But it's very risky, right? So what I recommend to do is do well on all the exams so that you're not relying on this sort of thing, right? So that you don't bank on, like, oh, I'm not going to study until the end of the class. It's never a good strategy. Okay. Any questions on that? Okay, so the final date is here. So oh, sorry, this should be 52. Oh. So this should be 52A and 52B, so I need to fix that. Okay. Okay, so that's pretty much it. Yeah. So any questions? Office hours. Office hours are going to be on Friday after this class. Okay? Yeah. You have to submit it to me. Yeah. It's not like a WebAssign thing or anything. It's like written homework. It's proofs. So the class about proofs, you're just going to be doing a lot of proofs. So I'll have you do some proofs. You hand them in. I grade the proofs, or the grader will grade the proofs, and then we hand them back. Yeah.
So I see here that you said you want us to use latex. Should we be typing these all?
Yeah. So this is a good. So now that you're transitioning to more advanced classes, this is a good time to start learning LaTeX, right? Or LaTeX, right? So LaTeX is a typesetting software for math. Okay. And if you have questions, come by office hours, and I can help you get you set up on that. Yeah. But I'm encouraging you guys to try and use LaTeX now. And so when I give the homework, I'll give you a tech file maybe, right? For if they're not just problems out of the books. I haven't quite decided yet, but if I do produce a tech file, I will give you guys the tech file so that you guys can use that if you so choose to type up your homework. Okay. Any questions on this administrative stuff? Okay, cool. This is on the webpage too. You can always ask me questions later. Okay, so this is a class on logic. And so logic is the study of strings of symbols and the interpretation that we give to them. Okay? So, and I guess we're going to start with propositions and formulas. All right? So, here we go. Let's see if this is good. And if this runs off a little bit, so I'm like, let me try and zoom out a little bit. Okay, so this looks better. Okay, so let's talk about propositions. So when I do a section, I usually make like a little box at the top here, and that's that indicates that I'm going to start a topic. So this is the topic that I'm going to start talking about is propositions and formulas. Okay, so let me give you a definition. So when I make a definition, I'll do something like this. I'll make a definition environment, or like some sort of definition thing, and then I'll define what I'm going to do. And the thing that I define, I'm going to underline. So a proposition so I'm defining proposition is a sentence which is either true or false. Okay, so it's a sentence where we can make sense of whether this thing is true or false. Okay, so let's start with some examples. All right, let me get rid of this. So I'm distracted by this. Okay, so I'm going to put so I said it's about strings. So strings is just a bunch of like characters put together, right? But then we give the characters meaning, right? So I'm going to put it in quotes. So here's an example. I'll put a bullet for the first example. So like 2 plus 3 is equal to 6. Okay? So this is a valid proposition. It's a sentence. It has a truth value. This one's false, right? 2 plus 3 is not equal to 6. So this thing evaluates to false. All right, so here is another example. Every prime number is odd. Okay, so a prime number is a whole number, a natural number. So a natural number is one of the numbers 1, 2, 3, 4, 5, and so on. Okay, so one of these whole numbers. Okay, and a prime number is a number whose only divisors are 1 and itself. Okay, so 2, 3, 5, 7, yeah.
Do you count
1 is not a prime number. 1 is a unit. Yeah, so 1 is technically not a prime number. So, So yeah, so 1 is not a prime number. We'll get into this too. So this is a good point. These are the type of questions that we're going to be talking about, is the technicalities of these definitions. So I'm kind of giving an informal definition, but let me just say that this is a proposition which evaluates to true or false. This one's actually false. 2 is a example of a prime number which is not odd, right? Okay, so we can give more complicated expressions, right? Things that don't have simple proofs. So let me do this one. So there do not exist natural numbers let's do x, y, z, n such that x times y times z is not equal to 0. And then I'm going to do this. This is my symbol for and. It's an ampersand. You can write and, A-N-D, if you want. It doesn't really matter here. So this is not equal sign. If you guys, it's not just like it's kind of like smudged, but this is supposed to be an equal sign with a line through it. N is bigger than 2, and let's put it down here. X to the n plus y to the n is equal to z to the n. Okay, so this one here is so if n was equal to 2, right? We know that there exists. So this one here, this condition here, just tells you that you know either x, y, or z is 0, right? This whole thing is going to be 0. Okay, so this is kind of removing that case. But if you look at like 3, 4, 5 triangles, right? So this is when n is 2. You can find numbers so that 3 squared plus 4 squared is equal to 5 squared, right? So this would not be true if n was not bigger than 2. But if you take n equal to 3, 4, 5, another number bigger than this, this turns out to be true. And this was posed in the 1500s by a guy named Fermat, right? And so this thing turns out to be true, but the proof of this is quite involved, right? And it was only proved in 1995, okay? So this was a very long thing, right? So this guy, said he had some proof of this, and the proof is so nice it doesn't fit into the margin of the page, whatever. But then it took till 1995, probably didn't have a proof. It took till 1995 for people to actually prove this. Well, this is a very simple statement, right? It's a proposition. So this one is a proposition. It evaluates to true or false, regardless of how complicated the proof is, right? This thing's either true or false. Okay? Okay, so let me give you another example. So every even natural number bigger than 3 is a sum of 2 prime numbers. All right, that fits on there. Okay, so let's think about this one here. Okay, so every even natural number bigger than 3 is a sum of 2 prime numbers. So let's think about this. So 4 is 2 plus 2. So I'm going to allow repetitions. 6 is 3 plus 3. 8. What's 2 prime numbers that add to 8? So 5 and 3. Right? There we go. Okay, let's do 10. 5 and 5. 12. 7 and 5. Okay? 14. 7 and 7. 16. So 11 and 5. Right? What am I at? 16, 18. Okay, 5. Did you say 5 and 13? Yeah. Oh, yeah. Oh, there we go. 2 of them. Right? 9 is not a prime number. Right? So 9 is divisible by 3. It's 3 squared. Okay? But you guys get the idea. So if you were actually going to check this with a computer, right, you could check it out for, indefinitely, right? So you go to a computer and you're like, okay, find 2 prime numbers that add to this even number. Okay, go to the next number. And do this, so on and so forth, and you try and go up further and further. Okay, it turns out that this thing seems to be true, but this one here we don't have a proof of, right? And this is called Goldbach's conjecture. And we don't know whether it's true or false. So if you were able to prove this thing, right, you'd be a rock star. Okay, so this one has been open, I think, even before the Fermat conjecture, or this Fermat-last theorem thing. So this is a very, if you were able to resolve this, so you guys get the idea? Is like, even though we can check it out for very long things, we don't have a proof of it. But again, this is an example of a proposition. This statement is either true or false. At some point, we're going to find a prime number where it's not this, or some even number that's not the sum of two primes, or it's true and there should be a proof. Okay. It's kind of a weird. It's a weird one, right? Okay, but it's still a proposition. It makes sense. It makes sense to ask whether this, the truth or falseness of this makes sense. Okay, and that's what makes it a proposition. Okay, let's give another example. Okay, so let's continue with these examples. So I'm going to move the slide here. It'd be nice if you do two or something, but if you guys want to go back to see one, just let me know. Okay, and I'll bring it back up. Okay, feel free to shout out questions as well. So the more interactive this is, the better it will be. Okay, so let's do another proposition here. So here's an easier one. There exists. So make sure, and then if I ever run up or I get off the page, just let me know, and I'll try and bring it back down. So there exists an even, or sorry, there exists a prime number. Okay, so there's a number which is prime. Okay, a 2. So this thing's true, right? For this one, we only need to check that we only need to find one example for this to be certified as true. Okay, but this is a proposition, regardless of its truth value, right? It's either a true or false statement. Okay, so let me give you this last example, which is a little bit dubious. Okay, so and I'll explain what I mean. Okay, so I'm going to show you how certain things can be a little imprecise, and we're going to try and make them more precise. So let me just say this. All positive numbers are squares. Okay, so a square is, there exists another number so that when you raise this to the second power, it's your original number. Okay. So this one is, so it's a proposition, but the meaning of it is ambiguous. So this one's a little ambiguous, right? So why is it ambiguous? What do we mean by all positive numbers? So what do we mean by this? Okay, so there's kind of two things that we could do. So we could either mean like natural numbers, or we could mean real numbers, right? Those are two possible interpretations of this. Okay, so if they're real numbers, then this is true, right? If they're natural numbers, this is false. Because, okay, so what do we mean by all positive numbers? Are we talking about positive real numbers? Are we talking about positive integers? What do we mean? So the domain over which we range is sometimes called the universe, right? So, and this depends on the universe. So, like in this case, like what's a positive number that's not a square? Like 3, 2, right? So in this case, n is equal to 2 is not a square. That is, if we're only considering squares where we're allowing multiplication by natural numbers. Okay, so we're only, it's a square by a natural number. Okay, so the context over which we consider a proposition is called the universe. The universe. So this is the definition of the proposition. Of the, Okay, so in order to make the proposition make sense, we need to specify a universe. Yeah.
Something, I guess, mental problem that I'm having with natural numbers. This seems like it's asking all positive numbers, so we would be inserting in between positive numbers all positive real values.
Yeah, exactly. That's exactly what's going on. Yeah.
But how are both statements not true? We're not looking at if the squares are real or natural. Are we just looking at the numbers themselves? Because 2 as a natural number is still a square.
You mean the square root? Yeah. Yeah. That's another statement that you could say. You could say, is it? Yeah. So that's another So it's still, yeah. So that's a good point, right? So you're saying that 2, it's a natural number, but if I consider the square root of 2, that's a real number, which makes it a square. Is that what you're saying?
Well, I'm saying, like, all positive natural numbers or squares could still be considered to be true if you're looking at all positive natural numbers as the numbers that you're looking at as squares, not necessarily squares of what? Like, what is it? Square root of 2 times square root of 2. Square root of 2 is a real number.
Exactly.
But it's not a natural number. But are we looking at
That's exactly
all
my point.
numbers that are squares
As natural numbers. That's exactly my point. That's exactly my point, right? Is that you need to specify over where you're allowing square roots, right?
Okay, yeah.
Right? So if you're going to allow reals to be square roots, then it's true. If you're not allowing reals to be square roots, if you're saying I'm looking only for natural number square roots, right? Then then it becomes false, and that's what I mean by this one. So here I'm only letting things range over natural numbers. Yeah, that's exactly what I mean. That's a very good point.
Okay.
Yeah. Okay. So all right. So let me just take a little interlude here to just kind of introduce some notation. Okay. So here, since we've talked about universes a little, I want to pause for a second and then talk about number systems that we're going to commonly use in some common universes. Okay? So here we'll do a little. So we're going to talk about universes of numbers. So universes are just sets. Okay? So sets are just collections of things. Okay? And I'm just going to write some notation down so that we can, and I'm going to come back to this later, but just to, it's the first class, so we have to set some stuff down. Okay? So here, see, so this is the set of complex numbers. Okay? R, this is the set of real numbers. So real numbers are the things that you used in calculus, right? So pi, e, square root of 2, everything on the real number line, anything that has a decimal expansion, okay? That's the informal definition of the real numbers. There's a much more rigorous and formal definition of the real numbers, and maybe if we're lucky, we might be able to talk about it at the end of class, okay? So there's Q. This is the set of rational numbers. So this is kind of a blackboard C, blackboard R, blackboard Q. Z, this is the set of integers. Okay, and let me just kind of show what these are. So one way of specifying a set is to kind of give a sequence like this. Okay, and then N. So, okay, let me give you a warning here for those of you taking notes. I'm going to write some stuff over here as well, okay? So, like, I kind of set up this page so that I'm going to write some more there, so you guys know. Okay, so this is the set of natural numbers. Okay, so the set of natural numbers, this is 1, 2, 3, the whole numbers, you know, numbers, numbers, right? Okay, if we were in France, right, they would include 0. We don't include 0. We're Americans, okay? So, for now, okay? So, so what is the set of rational numbers? So the set of rational numbers, so I'm going to tell you about set builder notation, okay? So the set of rational numbers are the things that look like P over Q such that, that's how you read this. So it's the set of P over Q such that P and Q, they're integers, and Q is not equal to 0. Okay? So they're just ratios of integers. And so let me tell you what this little symbol means. Let me go down here. Okay? This symbol here means an element of. Okay? So an element of. We'll see a lot more of this. So like X, an element of Q, means, this sentence means X is a rational number. Or an element of the set of rational numbers. So it's part of the club, right? The club of rational numbers. So this is this symbol, that's what this means. Okay? So for example, you know, pi is an element of the real numbers. That's a true statement. Or the square root of -1 is an element of the complex numbers. Okay, so the complex numbers, let me remind you what they are. They're the set of x plus I, y, where x and y are real numbers. And here, I is the square root of -1. Okay? So maybe you guys saw this a long time ago, right? But just going to remind you what that is. Okay, so these are the guys with the decimal expansion. These are you know, the whole numbers, but positive and negative whole numbers, including 0. Okay, so let me just give like another, just kind of to do this. We'll do more about this set notation. So I just want, this is like a first time. Yeah. Yeah. Thank you. Yeah. There? Oh, in the back. Okay, sorry. Yeah, you guys. I was like, there we go. Yeah.
So if PQ is element of Z, is that an and?
Yeah, that's an and. This is an and. You can write and. You can write, you know, your own way of writing and. You can write and A and D if you want. It doesn't matter, right? But here, this is kind of a formula that we have, right? Where this thing evaluates it, you know, once you have these things here, and this thing is okay. It's like not a, you know, this thing's true, right? So P is an element. So this is really P is an element of Z, Q is an element of Z, and Q is not 0. Then you form this thing, and then you make the collection of all those things. Okay? Okay. So let me give you one more just like set notation just for kicks, just so you guys can see some more of this set builder notation, right? And we're gonna do a lot more with sets, but here's another example of a set notation. So here's another example. So this is the X and R such that X is you know, bigger than or equal to 1. Okay? So this thing is read as such that. Okay? So it's like these guys such that thing. Okay? This is one way of doing this. So this is the set of real X such that X is bigger than 1. Okay? And then in the calculus notation, right, you guys would write this as 1 infinity, something like this. Okay? So it would just be that interval. Okay, so this was a quick thing. I just wanted to talk about number universes for a second because we'll come back to them. All right. We'll talk about sets more in a bit. Yeah.
For that one, wouldn't it be the same thing if you were to put x as an element of real numbers and x's are greater than or equal to?
No. So like here you have to. So this is the things that you're gonna like run over. So like, so you can't just put you can't just put and there, right? Because you have to have some. So like you have to kind of collect all the objects in the first part. I guess you could put something like this. This would be also equivalent. You could see the set of x such that x is a real number and x is greater than or equal to 1. This is also true. But you need to have something that like collects all of them, right? So we'll talk about this will get more familiar. I haven't told you all the rules that go with this. This is just a first initial look at this stuff. Okay? Okay. And there's several ways to specify sets, and we'll get back to that. Okay, I just wanted to remind you about those universes. Okay, so back to propositions. So we did this little interlude on things. We did our propositions, right? We did our propositions here. Then I gave examples of propositions here, and then we got sidetracked by this universe stuff. Okay, and I just wanted to say what some common universes that we could consider are. And now I want to give some non-examples. Okay, so let's talk about non-examples. Okay, so let's see, we're back here. There we go. Non-examples. So non-propositions. Okay, so here's one. Let's do this. 2 plus 3. We just do 2 plus 3. 2 plus 3 what? Right? 2 plus 3, it doesn't make sense to say whether this is true or false. It's just a number. We didn't say anything about it. Okay? Here's another one. Right? And this one's a little trickier. N plus 1 is greater than 3. Right? So okay, so let me just mark here that this is an expression. Okay, and this thing here, this thing is a formula, right? This is what we call a formula. Right? And its truth value depends on n, right? So its truth value on n. So this can range over the n in our given universe, right? So after specializing n to a special value, right, then we can say whether it's true or false. So for example, right, if n was equal to 4, right, then this thing here, so if we called this thing p of n, right, p of 4 is true. Right? If n is equal to, let's say, 1, right, p of 1 is false. Okay, so like here we could, it's like a function, right? So here I plug in things in my universe, and what it outputs is a true or false statement. Okay? This is a special kind of formula which is called a predicate, right? So it's okay, and so a formula. Okay, let me also say what this thing here is. So this n here. So this is sometimes called a free variable. It's free because we didn't really specify what it is. Okay. If we said something like for all n plus 1 is greater than 3, that would be called a bounded variable. And that thing, after we say for all n, right, and we specify the universe, right, then we can make sense of whether that statement is true or false. Okay, so so let me just say what a formula is. So definition. So a formula is a sentence So a collection of strings, it could be in English or it could be something more logical, right? Where after replacing variable symbols with objects of the universe, we get truth values. So it can evaluate to either true or false. Okay. So I forgot to set a timer. So what time does this class end? Do you guys? Okay, great. Okay, let me put in. Okay, so all right. So let's now. So I gave you guys that handout, right? And so now what I want you guys to do is let's go to the handout here. And so I want you guys to we'll take like maybe 5 minutes or so, and we'll talk about this first exercise here, right? So we want to talk about whether or not which ones of these are propositions and which ones of these are not propositions. Yeah. Okay, let me, who's missing the handout? There we go. For you. Okay, and just maybe now's a good time, if you don't know the person next to you, to introduce yourself. And then you guys can feel free to use any resource, living or not, for this exercise. Okay, and so once you just think about it, and then I'll come around and see how you guys are doing. Yeah. Yeah. I know you, so I'm going to compile you. It definitely makes sense, right? So, I mean, you can evaluate it, right? Someone could say that. You don't really care about the outcome of it, right? Just whether or not it makes sense. Yeah, whether or not you can make sense of it. Does it make sense for this thing to be true or false? So no, I'm not asking whether or not it's true or false. So we don't care whether or not we don't care whether or not it's true or false. We only care if it makes sense for us to ask whether it's true or false. So like, yeah.
I understand. So I just write it's true for it is a proposition, but it's.
Oh, okay, that's what you meant. Okay, yeah. Sorry, I didn't understand what you're saying. Yeah, exactly. No, this is a proposition.
Oh, yeah.
So you can determine whether.
I just.
Yeah. Good. 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 Anyone want me to check anything or? Yeah. Oh yeah, I don't want you guys. Just only one for now. So yeah, we haven't talked about these things yet. So 2, we have to talk about other things like connectives. And this is what I'm going to talk about. I'm going towards this. So, yeah, I just want to talk about number 1 right now. Okay. So anyone have any interesting comments on the first one? Let me put this back on. Up now. Okay, there we go. So does anyone have any comments or questions or? Yeah, you free to shout out, man.
Number 9.
Yeah, number 9.
So you can say
Yeah, exactly. But which is it? Yeah, so this is a very famous example. So this one this is what motivated this. There's a very famous theorem in logic called Gödel's incompleteness theorem. And if we get near the end of the class, we might talk about it. But if you think about this too much, you'll go a little nuts, right? But the incompleteness theorem, which this thing stems from, there's a statement that says, okay, well, if you have a set of axioms for a theory which are consistent, right, then there necessarily exists a proposition in that theory which is true, right? But you cannot arrive to it from a proof, right? So there will be some statement in there which you can formulate, which just so happens to be true, right? And you can't get there via, so what's a proof? A proof will be a sequence of logical inferences. So like you have to go from one step to the next step using these rules that you follow. So you have to kind of set up the game, right? But yeah, anyway, it's kind of this particular proposition is kind of self-referential, right? And leads to some issues. So there's lots of issues that'll come up, and this is kind of a cool one that happens. So it gets weird, right? But yeah. Anyway, it is a proposition, right? It does make sense to ask whether the sentence is true or false. It's just self-referential, but we don't really care about that right now. We just care whether or not it makes sense for this thing to have a truth value, right? Yeah, it can have a truth value, right? It makes sense for this thing to be true or false, but it's just self-referential. Other comments? What about number 10? Is that one true or false? So it's false because, yeah, well, exactly for the reason you said. I think this is what you meant. You meant to say 0, zero is a real number, right? So how do you determine if a sentence like this is false, right? Well, you just have to find a single example where it's false. And 0 is a real number. It's on the number line, right? 0 squared is 0. But is 0 bigger than 0? No, it's bigger than or equal to 0. It's actually equal to 0. So that's what makes this sentence false. But it is a proposition. It is a proposition. We don't care. Yeah, it is a proposition. We don't care, what the truth value is. We just care whether or not it makes sense to ask about the truthness or falseness of this. Which ones are not? So what is your name? That's not one. These ones here, these are exactly like the thing that we talked about. They have a free variable in them, right? And so they're formulas, in particular they're predicates, okay? So these things spit out truth values when you plug in particular values of x, okay? And then, I should probably be doing this here, yeah. And then give me that is definitely not one, right? Okay, so it's, I don't know, command or something. So, okay, and so that's what we did. So that's good. All right, that was fun. All right, we have a little bit more time. Okay, so let me go back and look at our example propositions again. Okay, so we started by looking at these propositions here. So we have our non-examples here. But we have so we had these propositions here, and then we had these ones here. So we had 1, 2, 3, 4, 5, 6 examples here, right? And I kind of want to talk about the little pieces that go into all of these things, because we're going to try and break down, we're going to try and like formalize everything. So our goal is to kind of break this down and to talk about all the pieces that go into propositions. Yeah. Oh, wow. Yeah, that's. Thank you, guys. All right. Yeah. So here were our. Where'd it go? Right here. Well, we had our examples here and here. Okay. Yeah, I saw someone's hand. Was that the same? Because I was. Okay. Okay. So, all right. And now, okay. So let's look at these things. So there's some common occurrences here. So there's something like every. So here it's like every prime number, right? There do not exist prime numbers. All right. Every. Right. There's an every there. Right. There exists. Right. So these things here are quantifiers. Okay. So they're telling us that we need to take one of these formulas. So here is a prime number, is odd, right? So those are two things, right? They're okay. Here are some more formulas, and they're joined together. So we have ands there. So this and, right? Every even, so is even. Well, this one actually has a statement is even in there. Is a sum of two primes, so there's like an equality in there. But is a prime number, that's another example of a predicate. So like you can take a number, and I can ask if it's prime, and it'll return true or false, right? There exists, so that's another quantifier, is a prime number. So all positive numbers, so for all is a quantifier. R squares, right? So that's another predicate. So let me go and talk about some of these parts. So some of the parts, so some of the components. Okay, so the formulas. So we had formulas. This is things that we talked about. So these were like x, y, z is not equal to 0, right? We had 2. We had 2 is or n is bigger than 2 was 1, and then we had things like x to the n plus y to the n is equal to z to the n. That was 1. Okay, so we have a bunch of different formulas that appear. So these have a bunch of different free variables, right? So there's predicates. Predicates are things like is a prime, is even, is a square, right? So these things, you can take something and plug it into there and get a truth value back. And there's these connectives. So what are the connectives? Connectives are like and. So you can take one proposition, you can take another proposition, you can and them together, and you'll get a new proposition. We'll talk about that. You can get or. You can take one proposition, take another proposition. You can logical or them together to get a new proposition. And you can not things. So like there does not exist, things like that. There exists, or you can say there does not exist, right? So this, you can take a proposition and you can not it, right? Or you take a formula and say not this formula. XYZ is not equal to. So that's the same thing as not XYZ is equal, X times Y times Z is equal to 0, right? Okay, and then there's quantifiers. So quantifiers were the things like for all, there exist. There's only two. There's only two. And they'll actually be given symbols, like an upside down symbol, and there's a backwards E symbol, right? For all and there exists. Okay, these ones will be given symbols too. This is an and, this is an or. The not is an exclamation point or something like this, right? And sometimes we would have symbols for this, like P of X, so that's the predicate. This is X is prime, or you could have E of X, X is even, things like this. Excuse me. So the goal now, the short-term goal is to formalize all this. So I'm going to kind of go over this again, but in more detail. Okay, so this is like a first glance over, and now we're going to go back over it in detail. Yeah.
Didn't we talk about every uniform?
Yeah, every. So this is the same thing. Yeah, exactly. For all. Yeah, that's a good point. So every is the same thing as for all, right? Yeah. There's other ways of colloquially saying it, but we'll attach many English words to the same symbol, and the symbol will have a particular meaning. So what we need to do is kind of get rid of the English in all of this. Okay, so next time we're going to start with logical connectives. All right, thanks. If you have any questions, come ask me after class.